Welcome to another video lecture. In this video lecture, we are going to discuss about the time response of a second order control system. Now, we already discussed the transfer function. The general expression of the transfer function of the second order control system is given by Cs by Rs is equals to omega n square divided by s square plus 2 zeta omega n s plus omega n square. Here omega n is the natural frequency of oscillation in radian per second, and this zeta it is zeta, the Greek letter, is the damping ratio. Now, in the previous lectures, we already discussed about the response of the first order system. The response of the first order system is always exponential, but the response of second order system, it may be exponential or it may be oscillatory. It depends on the value of this damping ratio, whether the response of this second order system is oscillatory or exponential. So the kind of response of second order system depends entirely on this damping ratio zeta. So this zeta is you can say is a measure of how much dominant the opposition from the system is to the oscillations in the output. So if the value of zeta is low, we can say that the system will oscillate. And if the value of zeta is high, then the system will not oscillate. In this case, the system output will be exponential. Now, since the output depends on zeta, let us take different cases in which we will discuss the nature of the response for different values of the zeta. Now, before going into this, let us calculate the roots of this characteristic equation of the second order system. So the characteristic equation of the second order system is s square plus twice of zeta omega n s plus omega n square is equals to 0. Now, it is a quadratic equation, and we know we have a quadratic equation a x square plus bx plus c equals to 0. The roots of this quadratic equation, there are two roots, x1 x2 is given by this formula minus b plus minus under root b square minus 4ac divided by 2a. So we can determine the roots of this quadratic equation of the second order system. So the two roots s1 and s2 given by minus b, so this 2 zeta omega n plus minus b square, so this will be 4 zeta square omega n square minus 4ac, so this will be omega n square divided by 2a, so a is 1. So you can further simplify this. So this will be you can take common 4 omega n square from this expression, and these two will get cancelled. So you will get minus zeta omega n plus minus omega n square root zeta square minus 1. So these are the two roots we get from the characteristic equation of the second order system. So one is minus zeta omega n plus omega n zeta root square root of zeta square minus 1, and the another root is minus zeta omega n minus omega n square root zeta square minus 1. So these are the two roots. So now let us discuss the first case. In this case, we have assumed that the value of zeta lies from 1 to infinity. So it is greater than 1 but less than infinity, and these are the two roots of the characteristic equation of the second order system. Now in this case, since the value of zeta is greater than 1, this discriminant d will be positive in both the cases, s1 and s2. This value d is greater than 0, hence we can say, and s2 is negative, and similarly, since the value of zeta is greater than 1, the s1 will also be negative. So we can say that both the roots are real since the value of d is greater than 0, roots are real and unequal and negative. So the roots of the characteristic equations are real, unequal and negative. Now let us suppose that these roots, values of these roots is minus k1 and s2 is equals to minus k2. Since both the roots are negative and real, we have assumed that the values are s1 is minus k1 and s2 is minus k2. So in this case, the transfer function will become omega n square divided by, since the roots of characteristic equations are minus k1 and k2, we can write s plus k1 and s plus k2. Now, what will be the step response of this second order system? So for the step response, the value of Rs is 1 by s. For the unit step response, the value of Rs is 1 by s. So in this case, the value of Cs will be, let me cross multiply this. So this will be omega n square divided by s plus k1, s plus k2. Now to calculate value of Ct from Cs, we have to do inverse Laplace of this. So we first need to do the partial fraction. So let us suppose the partial fraction is a by s plus b by s plus k1 plus c by s plus k2. Now here I am not calculating these values a, b, c, since I just want to know the nature of the output response. So I am just taking the inverse Laplace Ct, which is the inverse Laplace of this Cs. So this will be inverse Laplace of a by s plus b by s plus k1 plus c by s plus k2. So I already know that the inverse Laplace of a by s is a plus this inverse Laplace of this s plus k1, we already discussed this will be exponential function, and the inverse Laplace of this last term is also exponential. So this will be minus k2 into t. So this is the response of the second order system for the unit step signal. So here we can see the response is purely exponential. So let me summarize this. The response is purely exponential. This means this damping zeta is so high, this damping is so high that there are no oscillations in the output, and it is purely exponential. Now such systems in which damping is very high is known as the over damped system. So these type of system in which damping is so high that the output is exponential rather than oscillatory, such systems are known as the over damped system. Now this condition where we choose the value of zeta to be 1 to infinity, this condition is known as the over damping condition. So let me write here this over damping condition. Okay, so in the first case, when damping is high 1 to infinity, system the output response of the system is purely exponential, and this condition is known as the over damping condition. Now let us discuss the second case. In the second case, we assume that the value of damping ratio zeta is equals to 1. Now in this case, these are the two roots s1 and s2. Since the value of zeta is equals to 1, this discriminant d will become 0, and since the d becomes 0, the s1, the value of s1 will be, since the value of zeta is 1, so this will be minus omega n, and similarly when the zeta is equals to 1, this will become 0. So this again s2 is also minus omega n. So both the roots are same, or the roots are equal. We can say the roots are equal, negative and real. So we can say in this case roots are equal, real and negative. So when zeta is equals to 1, we get equal roots, real roots and negative roots. Now in this case, the value of the output on input, this value comes out to be omega n square divided by, since both the roots are minus omega n and minus omega n, we can write the equation s plus omega n, s plus omega n, and for the unit step signal, the value of Rs is 1 by s again. So this is for unit step input. So we need to calculate the value of Cs in this case. So the value of Cs, we are cross multiplying this with 1 by s. So this will be omega n square divided by s, and this will become s plus omega n whole square. This will be s plus omega n whole square. Now in this case, when we want to calculate the value of Ct from this Cs, so again we have to do partial fraction. So let us suppose the partial fraction is a by s plus b by s plus omega n whole square plus c by s plus omega n. Now again, I am not calculating these values. These are not important. We just need we just want to know the nature of the output response. So Ct will be inverse Laplace of Cs. So this will be inverse Laplace of a by s plus b by s plus omega n square plus c by s plus omega n. Now the inverse Laplace of a by s is a plus, now this inverse Laplace of c by omega s plus omega n we know. Let me write it here, that inverse Laplace of this 1 upon s plus a is e raised to power minus at, and the inverse Laplace of 1 upon s plus a whole square is t times e raised to power minus at. We use differentiation property in that case. So let me write it here, b, since the inverse Laplace of this square term is bt e raised to power minus omega n into t, and the inverse Laplace of this is simply e raised to power minus omega n into t. Again, as we can see, the response of this system is exponential. This is exponential response. But if we can compare with the previous example, the response is fast, or you can say the settling time is slow. Now what is settling time? Let us discuss in the next slide. Now if we plot the response of the second order system for both these cases, when value of zeta is equals to 1, when value of zeta is equals to 1, and when value of zeta lies from 1 to infinity. So we get this type of response as shown in the graph. Now when we increase the value of damping ratio, system becomes slow and it approaches to steady state value. Now this is the steady state value. This is the steady state value. This is the steady state value. Now the system approaches to the steady state value slowly, or we can say the system becomes sluggish. As the value of zeta as we reduces the value of zeta, system becomes fast, and the settling time is the time required for the system to reach the steady state value. Now from here, for zeta is equals to 5, we define settling time like this: when system increases and approaches towards the steady state value. So when it reaches the steady state value, that time is known as the settling time. Now the system approaches fast towards settling time as the value of zeta reduces, and at zeta is equals to 1, the settling time is minimum. So this is the settling time for zeta is equals to 1, so it is minimum. Now after this value zeta equals to 1, if we further reduce the value of zeta, system starts oscillating. So till zeta is equals to 1, system response is exponential. Still, let me write it here, till zeta equals to 1, system response is exponential. And after this, when we further reduce zeta, the system starts oscillating. So this value of zeta equals to 1 is the critical value. It is the critical value of damping ratio. This is the critical value of damping ratio, and hence this condition of zeta is equals to 1 is known as the critical damping. This condition is known as critical damping. I hope you understood this. Now let us discuss the third case. In this case, the value of zeta lies from 0 to 1. Now the roots are S1 and S2 given by this expression. Now in this case, since the value of zeta is less than 1, this discriminant will be negative. So in this case, the value of discriminant will be negative. Hence we will get the complex roots. Let me take negative sign common from these two expressions. So in this case, the value of S1 will be minus zeta omega n, plus, when we take negative sign common, it will become j omega n 1 minus zeta square, and similarly S2 will be minus zeta omega n minus j omega n 1 minus zeta square. So in this case we get complex roots. So I can say roots are complex, rather complex conjugate, but the roots will be negative, negative real part with the real part of the roots will be negative. So with real part negative. So in this case, when the value of zeta lies from 0 to 1, the roots are complex conjugate and with real part negative. So in this case, the value of transfer function is Rs by Cs is equals to omega n square divided by s. Let us put these values here, s minus s1 and s minus s2. Now in this case, when Rs is 1 by s, which is for the unit step input, we can determine the value of Cs by cross multiplying this Rs here, and by putting these values S1 and S2. Now I'm directly writing the value of Ct after taking the inverse Laplace, and I will derive the expression of Ct in the next lecture. So the Ct comes out to be CSS, which is the steady state value, plus some constant k e raised to power minus zeta omega n t into sine omega n square root 1 minus zeta square t plus theta. So this is the response of this second order system for this case when the value of zeta lies from 0 to 1. Now here we can see that due to this sinusoidal term, we can say system the response is oscillatory, but since there is a exponentially decaying term here, so we can say system will oscillate but with decreasing amplitude. If we draw this response, let me draw this response with respect to time. If we will draw this response with respect to time, Ct, and suppose this is the steady state value, CSS, you will see that the response will comes out like this. This will oscillate but with decreasing amplitude, and it will approach to the steady state value. So this type of system where the response is oscillatory but with a decreasing amplitude, so this is decreasing amplitude. So this type of system is known as the these oscillations are known as damped oscillations. Okay, so the response is oscillatory. Let me summarize this case. The response is oscillatory with the oscillating frequency. Oscillating frequency is this omega t. So this is the oscillating frequency, omega n 1 minus zeta square. So this is the oscillating frequency, and but the amplitude is decreasing. So we get damped oscillations. Such oscillations are known as the damped oscillations with the damped damping frequency omega d, which is given by omega n 1 minus zeta square. Now in this case, damping is not sufficient. We can say zeta is not sufficient to prevent the oscillations. Hence such systems are known as the underdamping system. So this case, when the value of zeta lies from 0 to 1, is known as the underdamping case. So this case is known as the underdamping because the value of zeta is not sufficient to prevent the oscillations. In the last case, case 4, the value of damping ratio becomes 0. So if we choose, we consider damping ratio zeta is equals to 0, then the roots S1 and S2 is given by these two expressions. In this case, when zeta is equals to 0, this will become minus j omega n, and this will also minus j omega n. So in this case, the roots will be complex conjugate with 0 real part. I can say roots are, this will be plus j omega n, sorry. So you can say roots are complex conjugate with 0 real part and purely imaginary. Both the roots are purely imaginary. So in this case, the value of the transfer function Cs by Rs is given by omega n square. Since the value of roots is minus j omega n and plus j omega n, I can write it s plus j omega n and s minus j omega n. Now for the case when Rs is equals to 1 by s for unit step signal, for the unit step input, the value of Cs is given by omega n square divided by s plus j omega n and s minus j omega n. So this will comes out to be omega n square divided by s. So this will become s square minus, or rather it will be plus omega n square. So again we can do partial fraction. So this will be a by s plus b by s square plus omega n square. So value of Ct is the inverse Laplace of Cs. So this will be inverse Laplace of a by s plus b by s square plus omega n square. So we can take inverse Laplace a by s. The inverse Laplace of a by s is a plus the inverse Laplace of this s square plus a square is sinusoidal term. So this will be sine omega n into t. So here we can see the response is purely oscillatory. So this, since there is a sinusoidal term with oscillating frequency omega n, so we can say in this case the response is purely oscillatory with the natural frequency of oscillation omega n radian per second. There is no opposition of zeta. Hence this type of system is known as the undamped. This type of system is known as the undamped systems. So this condition of delta is equals to 0 is condition known as the undamped condition. Now if we plot the response in this case Ct versus time, and let us suppose this is the steady state value Cs, you will get the oscillatory output with the constant amplitude without any decreasing amplitude. You will get the constant amplitude in the output without any decay. So such systems are known as the undamped system. So I hope you understood all these 4 cases of the second order system. Depending upon the value of damping ratio, system can be categorized in 4 categories: over damping, under damping, critically damping and undamped systems. So I hope you understood this. Thank you.